Determining the oxidation state of our atoms is a bad idea because when we look at an individual molecule in organic chemistry, the different atoms or the same type of element within a structure can have multiple different oxidation states, okay, depending on its bond nature. We could go through and go all the way back to Unit 1 where we talked about oxidation states versus formal charges, and you could calculate the oxidation state for every single atom within a structure. Also a bit tedious. Okay? So in organic, what we do is come up with a kind of quick rule of thumb to adjust. When we look at reduction, it is easiest to look at reduction as an increase in the number of hydrogen bonds. Okay, this is not hydrogen bonding as a force. We're literally talking about the numbers of hydrogens attached to our atom. Okay? We could also see it conversely as the decrease in the oxygen bonds. And this is coming back to the origins of reduction and oxidation as terms. Oxidation is an increase in oxygen bonds or a decrease in hydrogen bonds. Very typically they come paired. Okay, so if we see a decrease in oxygen bonds, almost always we are also seeing, where did it go? A decrease in oxygen bonds. We're also seeing an increase in hydrogen bonds, okay, within our organic structure. It becomes a little bit tricky because sometimes we don't see necessarily what our reagents are, so we have to be able to look at a single structure and decide what happened to it. Okay? So when we look at the reaction up here, what happened? Okay. We are increasing hydrogens to our carbons. So by increasing the hydrogen bonds, we've done a reduction. And we talked about reduction and oxidation in general chemistry. We never just said reduction, did we? We said redox. Okay, why do we always have to say redox? They have to happen together. And yet when we look at this reaction, we call it reduction. We don't call it redox. Why? It's not independent. They have to happen at the exact same time. This is organic chemistry. I don't give two craps about the other thing that's not organic. Okay? So I focus on the organic structure, the larger molecule typically, and I say what happened to it. Okay? Our cyclopentadiene here was reduced to cyclopentane. Okay? What happened to the hydrogen? The hydrogen was necessarily oxidized. Okay? But again, we keep our focus on the organic material. We care less about what's happening to the reagent. Okay, so in this case, we've done a reduction reaction. So we could look for our hydrogens. The other thing we could do is look for our oxygens. Okay, and one of the big kind of issues that pops up is that sometimes we don't see hydrogen or oxygen very obviously. So instead of looking at oxygen, we can switch that to be what? An electronegative element, and more particularly, a more electronegative element than carbon, where the chemistry is occurring. Okay? And we're typically looking at these occurring at carbon because it's organic chemistry. Okay? sp3 is not carbon in general. That's very specific.
Said more than carbon when we were talking about more electronegative than water.
More than whatever is present. So if we take this carbon here, that sp2 hybridized carbon, this is going to be a horrible, well here, I can fix it with an eraser. There we go. What if, it's still a pretty horrible example. What if we did that? Okay. We could look at the reference of hydrogen. What happened to our hydrogen? Okay, lost hydrogen, so we did an oxidation. Okay, we said that we could partner either thing. Okay, so if we lost hydrogen bonds, so we decreased hydrogen, we must have also increased an electronegative bond. What was the electronegative bond we increased?
Carbon to carbon.
Carbon to carbon. This was a carbon bound to a sp2 carbon. In the product, it is bound to an sp carbon. Is the sp more electronegative than the sp2? Yes. Okay. So it's all in reference to what's happening within the reaction. Does that get better at your question? Okay. Questions about that? Okay. This is going to become important on identifying what happened, because then you can narrow down the reagents that you can potentially use, and we will see tons of reagents come out of these. Okay. So you need to be able to look at it and say, this is reduction, these are the reagents I want. This is oxidation, these are the reagents I want. Okay? Kind of makes sense? Okay. Anybody want to see me solve for an oxidation state? No.
Wait, you're not going to test it?
No.
Then no.
Take a look at our carbon, central carbon on the far left. We want to look at homolytic minus heterolytic to get us our oxidation state. So we're going to take a look at the bonds connected to that carbon. Okay? We're going to break each of those bonds homolytically. That means the electrons will go back to their parent atom. So if we look at the top bond to our hydrogen, that bond represents 2 electrons. One of those electrons will go to the hydrogen, the other one goes to the carbon. I will then do that same process for every single one of these, annoyingly. Oops, and I screwed up that last arrow because it needs to be a half-headed arrow because we're only moving 1 electron. How many electrons would be around the carbon? 4. We've now got our homolytic cleavage. Okay. Minus heterolytic cleavage. Jeez. Okay. What does heterolytic mean? It's based on our difference in electronegativity. The electrons are going to go to the more electronegative element. Which is more electronegative, hydrogen or carbon? Carbon, which means we'll go back to our drawing and say the electrons in that bond go to the carbon, to the carbon, to the carbon, to the carbon, and we would end up with 8. This gets us a total of -4. Okay, what does it mean to reduce something? What happens to the oxidation state? It gets low. Okay. In this case, how many bonds do we have to that carbon? 4, and they are all hydrogen, which would suggest this should be the fully reduced state. What happens to our oxidation number? It's really small, really big negative number. Okay, so that makes sense. What happens if we shift to one of these other examples, and I'm going to make it a little bit more complicated. And actually I'm going to do that with black ink. Okay. We now want to focus on this next carbon. I now want to determine its oxidation state. How do I go through and do it? Homolytic. So with the hydrogen, where do the electrons go? 1 each. What happens with each of the other bonds? 1 each, and we end up with 4. Okay. Minus our heterolytic cleavage. So we'll go back and take a look at our heterolytic cleavage. Which one's more electronegative, carbon or hydrogen? Carbon. So it gets both those. Which one's more electronegative, carbon or oxygen? Oxygen. And oxygen. Which one's more electronegative, carbon or carbon? They're the same, which means it's going to split evenly. We end up getting a homolytic cleavage on that one, which means the number of electrons around our carbon comes out to be 3. We have 2 from the hydrogen, and we have 1 from our carbon hydrogen, and we'd end up with an oxidation state of +1. What happened is we went from our methane to our not methane. Sorry. Okay. Our oxidation state increased, which is oxidation. What happened to the number of oxygen bonds? Increased, which was oxidation. Okay. We could go through and apply that to everything else, and we could then evaluate for any given reaction by looking at every single atom in the structure that had some chemistry happen to and determine their oxidation states. Super exciting. You don't want to do it. You want the rule of thumb. Yes?
So the two bonds with the oxygen, those 4 electrons, you don't even put it in the equation at all. Looks like.
Those 4 electrons will not show up in the heterolytic cleavage because what happened to them? They all go to the oxygen.
It only goes off of that main parent.
Off of that center carbon. So we have to determine the oxidation state for every single atom. In this case, why are we only focusing on the carbon? It's our organic material. That's where we're trying to see our change.
So you can never have an oxidation state above 4?
If you go through and check all the way out to CO2, you're right. You'll notice it caps out at +4. Yep. And it would minimize out at -4. But you can hit pretty much everything in between, depending on what it's attached to. Okay?
It's 6.
I wouldn't even bother. You can ask me after class and I can try and calculate it. So, here's your quiz. I think everybody's got a paper. We've got 6 reactions here. Label is reduction, oxidation, or neither. You can talk to the people around you, see what you can come up with. Okay, so what changed in the first reaction?
Lost hydrogen.
This is where including the hydrogens can help out. We've lost a hydrogen, and we gained an electronegative element, which then means we did oxidation. Next one, what happened? Right. We lost a chlorine, so we lost an electronegative bond and gained an electronegative bond. What's the net result? Nothing. Neither. It's not oxidation or reduction.
Can you say because you can't? Oh yeah.
Okay. What happened in the next one? Sorry, there was a but.
Isn't it technically more electronegative?
So it's all in comparison to where the chemistry occurs. The chemistry occurs at that carbon. What did it do? It lost an electronegative element, gained an electronegative element. I don't care that those 2 elements have different electronegativities. It's irrelevant. They're both more than carbon. Yeah. Next one. What happened? We can look at it as a loss of an oxygen and gain of a hydrogen, which both lead you to reduction. In 4, what happened? If we again go through and include our implied hydrogens, that can help us see that what happened. Whoa, that low. We lost 2 hydrogens, which means oxidation. In 5, what happened? Okay. We've lost a hydrogen, and we gained a bond to our oxygen. We have oxidation. And then in the last one, I'm tired of showing everything, so I'm just going to write that one there. We went 2 bonds to oxygen, so that one we did double oxidation. Okay, we oxidized it twice. Okay? So being able to recognize those big changes can help us out because that can then whittle down some reagents that we can go through and use. Okay? You'll notice that the reagents that we end up using for all of these reactions will typically involve a metal, okay, or something in its elemental state. Okay? Why elemental states? They start as a 0 oxidation state, so if they react, what happened to their oxidation state? Changes, by definition, it's redox. Okay? If we go back to the one that was neither, what chemical allows you to do that reaction? H2O or H2SO4 will not do that conversion. It'll do the reverse. Actually, it won't even do the reverse. The only reason we need an acid is to protonate the alcohol to turn it into a good leaving group. It's our product. Okay? There's nothing to protonate over here. So water would work as a nucleophile. What's our other nucleophile? Hydroxide. If we used hydroxide, what mechanism would we be going under? That's not a mechanism. That's the type of reaction. It's an S. It is N. It's 2. Why is it SN2? Happens at the same time. How would we know it happens at the same time? What evidence? Okay, we can't say anything about, well, okay, I will switch my words there, okay, or eat my words there. If this happened in a two-step mechanism, we'd form an unstable carbocation, so it doesn't make sense to go through an SN1. Okay, so looking at our substrate, the substrate would suggest we should do an SN2. What about our hydroxide tells us SN2? It's a strong nucleophile. If we tried to do it with water, what mechanism would we be trying to do? SN1. We look at the substrate and say, can't happen, which means SN1 wouldn't work. We have to use hydroxide. Okay, make sense? That was kind of our quick exam 3 review. These are the kind of thoughts that you should be thinking about to try and get these reactions to go. Okay? So, reduction, the reagents with your alkenes and alkynes. I forget where I stole this picture from, but it's kind of a nice picture. We talked about this. Okay? Hydrogen is too small to coordinate to the double bond or react to the double bond on its own. Okay? So we can't get it reacting like a bromonium ion would. Okay? And it is also so small and so unreactive that it won't react with the alkene or alkyne directly on its own either. Okay? So what needs to happen is we have to introduce a catalyst. It ends up being a metal catalyst, typically platinum or palladium. You can also see nickel. Lindlar's catalyst, which I'll talk about maybe talk about in a second, is also platinum. Palladium. Okay? So we have a metal surface. What do metal surfaces tend to shuttle? Electrons. We have a really great source of electrons in the double bond. So our pi bond can coordinate to the metal surface. At the same time, hydrogen will coordinate to the metal surface. As long as those two reagents are close enough on the metal surface, what can happen is the metal will facilitate the transfer of hydrogen across to one of the atoms of the double bond. Okay? That then prevents the coordination or removes the coordination of the alkene to the metal surface. Okay? The next hydrogen will react very, very swiftly with our carbon, so swiftly that what happens to the sigma bond? It does not rotate. Okay? And the result is we end up with the syn addition. Okay? So no rotation. All of these or except for that last one, the sodium and the ammonia, all of them with hydrogen gas function the same way. Okay? Anybody see a potential issue with the speed of this reaction? Hydrogen is small and what phase? A gas. Your alkene is typically liquid, so multi-phase systems only react to the interface, so that's going to slow it down. And to get that reaction to work, what do we need? A metal, which is solid. We have a 3-phase reaction occurring. Okay? That slows down the kinetics of the reaction because we have to get all 3 phases into the same place where they can then interact. Okay? So we can up the pressure, we can up temperature to increase the motion of your particles so that they start to mix a little bit better. We can violently mix these solutions to get them to mix as well. Okay? All of those things are things that will contribute to the reactivity. Yes?
So I feel like we asked this before, but what does Rainey refer to?
Rainey is the name of the person that discovered the catalyst. That's it. And we haven't asked that, or I don't think that question's been asked yet. It's just the name. Same deal with Lindlar catalyst. It's the name of the person. Okay? In all cases, we're taking a pi bond and coordinating it to the metal surface. Where do pi bonds show up? P orbitals. What functional groups have p orbitals? There's a really easy one. Alkenes. The next really easy one. Alkynes. Carbonyls, which show up in carboxylic acids, in aldehydes, in ketones, in esters. Okay? There's carbon-nitrogen double bonds. Okay? All of those will react under the proper conditions with hydrogen gas and a platinum catalyst. Okay? So one of the big issues with those catalysts is they are not particularly selective. Okay? So they will react with all pi bonds. That's what we're saying, no selection. By changing the pressure and the temperature, we can get some selectivity and we can favor one reduction over another. Okay? But that's going to depend on slightly more advanced chemistries that we'll see in second semester. Just want you to be aware of the complexity of those. Okay? It's a very non-selective reduction. Okay? Two of these pop up as being interesting. Lindlar's catalyst and sodium with ammonia. Okay? What makes those interesting?
Sodium doesn't really exist outside of
One
water.
base.
Sodium, super reactive as a metal, and we'll address that in a separate case here. But you're right, that actually drives why this reaction's happening. What is special about those two reagents? What would happen if I take an alkene and react it with hydrogen gas with Lindlar's catalyst? If I take an alkene and react it with hydrogen gas and Lindlar's catalyst, it doesn't react. Hydrogen gas and Lindlar's catalyst will only react with alkynes. It will not react with alkenes. We have some selectivity now. The pi bond of an alkene cannot react with whatever's happening with our Lindlar's catalyst. Okay? What's happening with sodium metal and ammonia? What happens if I take sodium metal and ammonia and react it with an alkene? Again, nothing happens. Okay? What is different about those two reagents and the products they form? One's a syn addition and one is an anti-addition. Okay, so we end up with different different regiochemistries for our double bond. Why would we get different chemistries? Different mechanisms. Lindlar's catalyst happens to be based off of palladium. How did hydrogen add to the double bond in the presence of a metal? It does a syn addition. Okay, it adds to the same side. If we take this alkyne and I add hydrogens to the same side, what is that going to do to the R groups? Pushes them the same way, and we end up with the cis product, okay, for our alkene, okay, which is also a syn addition if we reference how we did the addition. Okay, we can call this a cis product because it does have the alkene, so we can still actually refer to this as the cis product. Okay, or the Z product. Okay. And almost all of those addition reactions, what do we end up finding? We get the syn addition of our hydrogen. And yet, when we move to sodium metal and ammonia, we get the trans product. What does that mean? Something has to allow for free rotation. Okay? When did we typically see free rotation? The formation of a carbocation. Okay? So something about that mechanism is generating a carbocation that can allow for free rotation. That free rotation is then going to give us the trans product. Why would it not give us the cis? Trans is more stable than cis. So in all of our reductions, we end up forming, or reductions of alkynes, we end up forming a cis double bond, at least at some stage. Okay? Which is unstable. Okay? That is our least favored double bond. And yet if we go through and mix it with something else, we can get the trans one, and the trans one is more stable. Okay? So now the question becomes is how and why do these work? I don't remember if I've got nice pictures on this. Give me a sec. Ignore all that. Oh, I don't have nice pictures. But I do have a stepwise mechanism for that one. So what is Lindlar's catalyst? Lindlar is a palladium catalyst. But if we just use palladium, what happens? It's not selective, and what happens to the alkene as soon as I form it? it reacts again. So we have to somehow alter the palladium such that it can't react with the alkene. Okay? What happens if, say, I don't know, you were trying to eat food and somebody did something that prevented you from eating more? You might say you were not necessarily full. What could someone do to prevent you from eating more food? Okay? There's still food out in front of you. When are you going to look at that food and be like, no thanks? So full doesn't work because that's you don't want to eat more. What is happening to prevent you from eating more? Why would you be grossed out? Something is wrong with the food. It has been poisoned. Guess what Lindlar's catalyst is? It is poisoned. Okay, so we can refer to it as a poisoned catalyst. Okay, what do we poison it with? Okay, I find this particularly annoying. Tons of different things can poison it, and depending on what question you see, you'll see varying different poisons being added. Okay, in all cases, we're taking a divalent metal, or all cases I've seen. So a metal in its +2 oxidation or +2 charge, and then being combined with some -2 charged species. I've seen it as a sulfate, and I've also seen it as a carbonate. Okay. So the one that I can think of off the top of my head, barium sulfate, works as a poison to prevent the further reduction of the alkene. Okay. So if you look at a list of reagents and you see hydrogen gas, palladium, and something else, stop at the alkene. You don't see that something else, reduce that all the way down.
What's causing it to be poisoned, or how does that react? Like, does the...
I'm going to really pull this is the end of the semester card, and dodge the question that way. Okay. I'll look it up and we can talk about it later on how exactly that mechanism is working. Okay. So Lindlar's will not react with alkenes. Okay, it will only react with our alkynes. Sodium metal in ammonia will only react with alkynes, again, not with alkenes. So we've got kind of our summary up here. Hydrogen with a metal, be it platinum, palladium, or nickel, you're doing a reduction down to the alkane. Okay. Officially a syn addition all the way down. This structure was not the greatest to show because it's very hard to see how we did the syn addition. Okay. If we had an alkyne, okay, again, hydrogen with platinum or palladium on their own, or nickel, full reduction. Okay, all the way down, and we'd end up doing what type of reduction or what type of addition? Syn addition. Here we can see it a little bit cleaner with the reagent I picked. Okay. When we move to Lindlar's catalyst and sodium and ammonia, Lindlar's, through a complex mechanism, will stop at the alkene because it is poisoned. It has been prevented from functioning. You may see that written as platinum or palladium with something. You may also see it as plain as day as platinum poisoned. Okay. They're all saying the same thing. It can't react with the alkene. So when we do the reduction of our alkyne, it'll go to the alkene first and then it stops. With the other ones, it continues to run. The other one is sodium with ammonia. That one's a fun question to toss out there because the end result is that we end up with the trans double bond, which is not easy to do with our standard reductions because our standard reductions involve the addition of hydrogen, and hydrogen is so unstable it has to get added in a syn fashion. Okay? So what is going on with the sodium and ammonia? Okay. Said sodium was super reactive. Okay, sodium metal. Why is sodium metal super reactive? Describe the Lewis structure for sodium metal for me. One valence electron. What is sodium metal going to act as? It wants to get rid of how many electrons? One electron, so we're doing a radical reaction. Okay. So what does that one electron react with? Whatever's the most reactive electron from somewhere else. If we take a look at our alkyne, where's the most reactive atom or bond? Atom or bond? bond? The pi bond. The result is that we end up forming whoops, that should not be a capital A. Okay. What is special about this structure? It's got a free electron. I would argue there's actually something more important than that free electron.
You went from an SP to an SP2.
True, that's also changed. Keep going.
You don't have an octet.
We're missing an octet, true.
You have a covalent bond.
Here's our hint.
Sodium?
Yeah, so
We have an ionic bond. What's the deal with ionic bonds? That is better represented as, what did we just find as our most reactive thing? A negative charge. What do we need to find? Something positive. Where do we find something positive? Well, sodium does a weak interaction. Where do I find something? Hydrogen's found where? On the ammonia solvent. And what happens? And we would end up with, whoops, let's go with our right colors. Our radical, R, and hydrogen. And then the ammonia would get drawn as, sorry, there is a dot there, it just didn't show up. We would have NH2 minus. NH2 minus is a stupidly strong base. Why would this reaction ever occur?
The negative charge of the carbon is more reactive.
The negative charge on a carbon is an even stupider, stupidly strong base. We're actually decreasing reactivity by making a negatively charged nitrogen. Do we have a final product yet? No. Now what's reactive about this structure? The radical, what can happen? Another sodium can come into play, donate the electron in, and we end up forming another anion. That other anion can then pick up another hydrogen from our ammonia, and we get the full mechanism drawn stepwise all the way out. Right. Yeah, don't do that either. Okay. We end up getting our trans product almost immediately. Okay. We're trying to get those R groups as far away from each other as possible, and because as soon as the sodium reacts, what happens to the pi bond that was keeping them away from each other? It's now weakened, it can pop, and those R groups are going to pop away from each other, not towards each other, with the breaking of that last pi bond.
So is the sodium a catalyst?
The sodium is not a catalyst in this case, because what happens to the sodium by the end of the reaction? It ionizes, it becomes sodium ion. Okay, so it is not a catalyst. It is required for this reaction to occur. Okay. This will become a little bit more relevant in second semester, but keep a close eye on that reagent. And now let me draw a second reagent. What is the difference between those two reagents? The bottom one is a strong base. The top one is a reducing agent because we have sodium metal. Okay? Very similar in structure, drastically different in chemistry. Okay? They are not the same thing. The bottom one is a product or side product of the top one. It's still not going to do anything to an alkyne, anything to an internal alkyne. Okay, why did I add that last statement about internal alkyne? What happens if it's terminal? Well, yeah, it reacts. What is it? How does it react? The alkyne acts as an acid. Why can the alkyne act as an acid? That carbon is sp hybridized. It is much higher in electronegativity than a normal carbon. It can steal the electrons away from the hydrogen relatively easily as long as we add a stupidly strong base such as sodium amide. Okay? Why would we do that reaction? What did we make? A negative carbon. Negative carbons are not easy to come by. We now have a carbon nucleophile. This becomes helpful because we can now do structure enlargement. Okay. This also shows up, unfortunately, in what's known as a Birch reduction. Okay? You're not responsible for it, so don't panic. I just want to make sure you're aware of it. Birch reduction will do the same thing, or same type of thing. It'll reduce the double bond of an aromatic ring. Okay? And you'll end up with that product. We will talk about that in second semester if you decide to stick it through with me. If you don't stick it through with me, you'd better talk about it in your other second semester class because it's an important reaction. Okay? As far as the mechanism goes, if you're interested, do the same thing. It's the same mechanism. The only thing that becomes a little bit more complicated, resonance. There's some resonance contributors in there that actually stabilize and cause that product to end up forming. Okay. So that is it pretty much for our reduction reactions. So go back to our summary here. You're responsible for knowing those reagents and what they react with and how they produce products. Notice up here, I addressed with hydrogen and platinum or palladium that we could react with carbonyls. Do you see any carbonyls on this slide? Guess why? You're not responsible for it yet. Don't worry about it. Okay? Just want you to be aware of that issue. Okay? But you're not responsible for those reactions yet. Okay, now we gotta do a bunch of advancing. Whoop, too much advancing. Now we'll do a shift into our oxidation reactions. This is a big, nasty kind of spider slide starting right there in our middle. We're taking that structure and we are putting it under various conditions. You notice that this is spiders out, say to the right. Okay, anybody know that functional group? It's an epoxide. Okay, it's one of those kind of gray area functional groups. You're kind of expected to know that it's an epoxide. You aren't really expected to be able to name it. Okay, the epoxide is now a reactive molecule because three-membered ring. Okay, that structure wants to break open. So what do we need to help cause that to break open? What do we need? General class. We need a nucleophile. Okay? So what happens up here? What's our nucleophile? We have an oxygen. What's the nucleophile down here? An oxygen. What's the difference between those two reactions? Acidic or basic environment is our first tip off. The top one is under acidic environment. I have no idea why the 2's there. Ignore the 2, please. Okay. And basic environment. Okay. What else is our difference? Which makes that a strong base and strong nucleophile. What's our nucleophile up here? Weak. If we go under a weak nucleophilic condition, we get a slightly different result than if we go under strong nucleophile conditions. Look at the product difference. Where does the nucleophile attack? Opposite locations of our three-membered ring. Okay? Both of which are backside attacks. Okay? Which should have been drawn correctly, yes. Okay? So that is important chemistry to realize. You should be able to recognize the upper one, okay, because that's our standard mechanism from our bromonium and our mercuronium ions. Okay? We attack the most substituted position with our nucleophile. The bottom one becomes a little bit trickier. We'll talk about the conditions that get you there. Going back to our, actually to get to the epoxide, you'll typically see the reagent used. Okay? Everybody loves this. I'm not a big fan of it either, but it's the way it's written. You'll almost always see it written as mCPBA. Okay? And that's because M stands for the element. Well, C stands for carbon, P stands for phosphorus, boron, and A. What the hell does that mean?
Is M just like a general structure?
It's a common name. It's the abbreviated IUPAC name. because if we draw out the structure, it's too big and we're lazy. So we end up writing out the formula, or not even the formula, the abbreviated name. Okay, much like we do with, say, THF, which is tetrahydrofuran. Same thing's happening here. Okay, except when we did it with THF, we did it with a solvent which was pretty innocuous. It didn't do anything. Unfortunately, mCPBA, super, super reactive. It's what forces the epoxide reaction. Okay? Metachloroperoxybenzoic acid. Which sounds really big. It's not that bad. Okay? After that, we've got 3 other reagents that you're required to know. Permanganate, osmium tetroxide, and ozone. Okay? Osmium tetroxide, pretty much if you see OSO4, just make it the diol. Turn the alkene into 2 oxygen bonds. Done. Move on. Okay? Don't stress about what the other reagent is, because 9 times out of 10, they don't show the other reagent. Okay? I will say that if you're working homework and smart work, they will have you pause at the intermediate of reacting OSO4 with it to actually draw out that structure. And then they'll say, then you add this, and the next step of the reaction happens. Okay? So smart work's a little bit of an exception there. If you see OSO4, diol. Okay? Diol meaning 2 alcohols. Notice, where are the alcohols? Same side. It's because it is a syn addition. Permanganate. Permanganate's an awesome reaction because, look, there's 2 reagents, and of course they give us 2 different products. What are the condition differences that you need to be looking for? Acidic and basic is one of the big tip-offs, not always found. Temperature and concentration are the big ones. If you see hot and concentrated, okay, what's the big difference? What did we do? Take it a step further than that. It's not just that the ring is broken. I like where you're going with that. What do you mean 2 double bonds with the oxygen? Lots and lots of oxidation. You oxidize the crap out of the reagent. Okay? Is that what you guys were saying back there? Yeah. Okay. What happens if under cold and dilute conditions? You only mildly oxidize it. Okay? Ozone. Ozone goes through and does some crazy, weird, but interesting chemistry. Okay? Again, this is one of those things that you kind of just need to know. Almost everything on this slide, it's just stuff you need to know about the reagents. Okay? When ozone reacts with the double bond, you form this crazy, weird, cyclic 5-membered ring with 3 oxygens within it. Depending on what you then follow that up with in a step 2, oh, I now remember that. Never mind. Okay? You can go under reductive conditions or oxidative conditions to change the results. Okay? Which is awesome, because if we react ozone across, we end up with an oxidized product, and yet we're calling it reductive conditions. It's reductive with respect to the fully oxidized product. Okay? So if you see ozone with DMS as your big tip-off, don't fully oxidize it. If you see ozone with pretty much anything else, oxidize the crap out of it. What do we mean by oxidize the crap out of it? Attach oxygens while removing hydrogen. If there's no hydrogen to remove, can you oxidize? No. Okay? So how could I change this structure, my starting alkene, to make sure I only get 1 product with ozone, regardless of which conditions I run under? Add another CH3. There's now no more hydrogens at that carbon, which means when we go through our first step, our product takes us here. When we cleave open, we would end up with our CH3 up here. We would then try to do the oxidative conditions further, but are there any more hydrogens to oxidize? Nope, so the reaction stalls there. Okay? So our reductive versus oxidative conditions really comes back to the presence of that extra hydrogen. Okay? Interesting feature, where have we seen this oxidative product before? Oh, interesting, right next to it, permanganate. Someone like planned the slide. Okay. It's right next to it. Both permanganate under acidic conditions and ozone under oxidative conditions get you the same product.
Could you also use the polyoxide state to form other epoxides too?
No, and that comes from what this structure means, and ultimately, because you're going off of the acid nomenclature, the reactive part of mCPBA is actually not the M, the C, the B, or the A, it's the P for peroxy. What is the structure of a peroxy? It is an oxygen-oxygen single bond. That is the reactive part. That bond is your peroxy. That's the reactive one. We don't have a peroxy forming in either of those. We're not going to talk about that, but it's there. Okay? So, our mCPBA synthesis. Okay? If we look at how this reaction works, okay, there's a crap ton of slide or arrows that can move through this reaction. That tends to confuse people. Okay? We have either a sequential mechanism or a concerted mechanism. And it would have been nice if I'd added some pieces on here. We added an R group and an R group. If we were under a sequential mechanism, where would those R groups be in our product? Sequential. They can be either direction. So I would end up getting two products, putting with them on the same side, and, because I'm horribly lazy, and with them on the opposite side. So a sequential mechanism will get both. Why? You break the pi bond, now what can happen? Sigma bond rotation, we could get both products. Okay? Under a concerted mechanism, what's happening? Okay. Both bonds of our epoxy are forming at the exact same instant, which means what happens to the sigma rotation? There is none, which means the stereochemistry of our starting material stays the same. The R groups have to be on the same side, and I end up with one product. Well, how do we know which one happens? Okay. We don't actually draw, and this is one of the things that students tend to panic about. Oh, well, now I got to draw and predict which one. No, absolutely wrong. What happens is someone said, I think it's sequential. I'm going to go into the lab and test it. Shoot, I'm wrong. Okay. Now I got to prove why I'm wrong. Okay. And usually what happens is they prove why they were wrong and then go back and say, well, actually, I meant it was concerted, and that's what I'm going to publish now. Now everybody thinks I'm a genius because I got it right on the first try. Fucking load of crap. Okay? But that's what's happening. Okay? We go into the lab and we find the concerted mechanism is the only mechanism that's happening. We do not get sigma rotation. Okay? So no sequential products come out of this. And I wanted this eraser. Okay? So now we need to come up with a mechanism to show both of those bonds forming at the exact same instant. Okay? To come up with a mechanism, we need to look at those two reagents and say, where's the reactive bond? What do you see as the reactive bond? Pi bond. Okay, which pi bond? Because I see two. Okay, why would the carbon-carbon be more reactive than the carbon-oxygen? So I'm saying some people shake their head no. Why are you saying no? You're saying carbon-oxygen is more reactive? Why? What causes reactivity? What makes it higher in energy? Charge. Where do we get charge from? Difference in electronegativity. The carbon-carbon double bond, is there a difference in electronegativity? No. Is there a difference in electronegativity between carbon and oxygen? Yes. Interesting. Our highest potential reactivity, if we're going to focus on our pi bonds, is likely going to be the carbon-oxygen pi bond. So we could take those electrons and move them where? We would more than likely move them directly to the oxygen. Why? Oxygen is more electronegative. Would we expect those electrons to do anything with the alkene? Why not? The alkene is full of electrons. It doesn't make sense for those electrons to react with more electrons. The direct repercussion of those electrons moving to the oxygen is that what happens to the carbon? It becomes positive. Does carbon want to be positive? What does it need? Electrons. Where are their electrons? Ooh, we heard two good answers come out of this. I heard the alkene, yes, there are electrons there. Okay. One thing we want to hold on that for is we know what our product is. What does the alkene react with? Oxygen. While the alkene could potentially share electrons with that carbon, does that get us closer or further from forming the official product? Further. So probably not the alkene in our mechanism. Other people suggested oxygen. Why would the oxygen be a more likely source of electrons than the alkene? It's closer. That oxygen is significantly closer to that carbon of our carbonyl than it is to the alkene. So those electrons can share there. We've stabilized the carbocation. Awesome job. I love it, guys. What happened to the oxygen? Don't like that so much. You made the oxygen positive. Where does that oxygen need to get electrons from then? The other oxygen. But now what happens? We broke a sigma bond. So when we had the positive charge on the oxygen, how many electrons did it have around it? Let's draw out that result to help us see what's happening here. So our structure at this point looks like we had a negative charge up there, and we had the positive charge here. How many electrons around our oxygen? 8. Has its octet. Okay. So we might say, well, I need to bond to oxygen. I got electrons. Let me put them up there. But what's the problem? Have its octet. So that's not a reactive oxygen with the alkene. So that oxygen needs to get electrons from somewhere else. If it gets them from the pi bond, we just made that. That defeats the purpose. So it only has one other place to get electrons from. That sigma bond. And yes, you're right. That absolutely breaks that sigma bond. But this is a reaction. We will be making and breaking sigma bonds. That's allowed. That's why it's a reaction. What is the direct repercussion of breaking that sigma bond, though? Whoops. We would end up with that oxygen being positively charged. Well, we had a positive oxygen before. What's the issue with this positive oxygen? It actually hasn't achieved its octet. It is electron deficient as a positive charge. Do we have another source of electrons? The alkene can share electrons up, initiating that whole stabilization effect. Okay? But now what's the issue? Whoops. No, I did that right. Our oxygen has a positive charge and we have a positive carbon. Okay? Both of those are going to be problematic. Okay? What's your weight?
Didn't you get rid of that positive charge there?
Oops. Yes, you're right. Sorry. Okay. We have a carbocation. Okay, so we stabilize the oxygen and we have this carbocation. What can I do with that hydrogen? What if I take the electrons away from that hydrogen and give them where? Could give them to the oxygen, but ultimately what do I want? I need to go to the carbon. If I take them to the oxygen, I have a carbocation, which means rotation, which we said doesn't happen. Those electrons must, instead of going to the oxygen, go straight to the carbocation. But now I have H plus chilling out in the universe. I wish there was, say, a source of electrons really close by. And guess what we've done? We drew a bunch of arrows that explain the formation of the epoxide functional group with 0 bond rotation. What do we have? A concerted, valid mechanism. Right? And that all came back to evaluating positives and negatives and slowly tracking through what happens at each of those stages. But what if this happens? Okay, what's the result? Ooh, that makes something else. What if this happens? Oh, that makes something else happen. Okay? It is a cascade of effects that ultimately comes all the way back to positives and negatives. Find your most positive, find your most negative, do whatever you got to do to fix it. Okay? The other thing that is important within this mechanism, the driving force for allowing us to decide that this is a good mechanism, we know what the answer is. Okay? Mechanisms are not made up out of thin air. We ran a reaction, we saw a reaction occurred, we have to explain that reaction. The power of mechanisms then comes from saying, I've gone through and done this. What happens if I change the conditions? Do I get something that I can still predict on? If yes, awesome, the mechanism holds, that's what you learn. And guess what? It happens a bunch. So that's what you get to learn, okay, or memorize. Ultimately, what you're responsible for in the epoxide formation, you are using mCPBA. Okay? I gave you a general form of mCPBA. I said the reactive part was the per-oxy bond, the oxygen-oxygen single bond. Okay? mCPBA drawn out as a big, large structure. That piece looks kind of like benzoic acid. I need a peroxy. There's my peroxy. Metachloro is saying at the meta position I have a chlorine group. For those of you that looked really heavily at the nomenclature within whatever that was on our benzene rings, that is the meta position. Do you need to know that for this exam? No. Okay? But that is mCPBA. Do we really care about the chlorine or the benzene ring? No. Your focus is out on that peroxy acid functionality. That's the chemistry of your epoxide formation. Okay? Syn addition, form a ring. Oh. Go away. Nope, come back. What's an issue with epoxides? We're making them by reacting them with pi bonds. How do pi bonds react? Above and below the plane of the pi bond, which means 2 products. Every time, okay, we get the potential for 2 products. So if we look at this starting material and we try to do an epoxidation reaction on it, react with mCPBA, we get 2 products. With the epoxide below the ring, epoxide above the ring. If only one of those is chemically active, what is the maximum our percent yield can be? 50. Okay? And we can think back to the lab and you're like, oh, well, 50% in the lab isn't bad. Okay, now let's switch it, 50% in lecture. That's not the greatest. Okay, we'd like to get a little bit better than that. So as a synthetic mechanism, this is pretty horrible until some jerk-off came along and found out that he could change the reagents during the epoxidation reaction to force one epoxide over the other. So we can improve our yield above a 50% selectivity. Okay? That guy is known as Sharpless. You can thank him later. He might actually still be alive. Okay? You use a titanium reagent, and then you also use a chiral material. Okay? Optically pure. That optically pure reagent works within the mechanism to force only one of the possible epoxide products out of it, depending on which of those chiral reagents you use, be it the positive or the negative. just be aware of it. That's about it. So why epoxides? Epoxides show up all over the place. Okay, what we've got up here are a whole bunch of precursors to biological molecules that have epoxides within them. Okay, so biochem uses these functional groups to do chemistry. If biology uses it, we need to use it to be able to generate chemicals or drugs for humans to interact with. Okay, so how does it potentially react? Under basic conditions, what happens? Okay, we're going to ignore half of this. What do we have? What's the most reactive thing? The negative charge is kind of the most reactive thing. What do we need to find? A positive charge. Where is there a positive charge? Okay, there is no formal positive. Is there a partial positive? Okay. The hydrogen potentially, but then what would we produce? You'd perform a negative charge on that carbon, which is only going to crunch that down even tighter. You're putting electrons near electrons. So the hydrogen's not going to work very well. What did you suggest? The carbon. The carbons of the epoxide ring. What happens if that nucleophile comes in and attacks one of those carbons? The ring is going to break open. Which bond would break open? The carbon-carbon or the carbon-oxygen? Carbon-oxygen, because a larger difference in charge, because oxygen is more electronegative than carbon, and our ring would bust open. The result is we end up with the nucleophile. We have our oxygen, we have our R group, and we have our hydrogen. I want more details. What? Oxygen is negatively charged. What can you tell me about oxygen as a negative charge? Does this reaction work? Why not? OH is a horrible leaving group. We cannot form a negatively charged oxygen easily. How do we get this reaction to work, the purple one? We had to add an acid to catalyze that reaction. Okay? So that reaction is horrible on its own. How can we force this reaction to go? We could add an acid. That's the next mechanism. Sorry, we can still get this one to work. In the previous case, hydroxide was a bad leaving group because it's leaving into an environment that is more stable than the hydroxide. That means the hydroxide immediately reacts. What if the hydroxide left into an environment that was less stable than the hydroxide? Then it's okay as a leaving group. So what does that mean? This nucleophile needs to be much more negative than the oxygen. Meaning the nucleophile needs to be super strong. It's the only way we get this reaction to work. If it is a super strong, we'll come back to that, bad idea. Okay. If we have a negative nucleophile, or a strong nucleophile, where would it attack? The least substituted or the most substituted position? The least substituted, because what's at the most substituted position? A bunch of electrons. So our strong nucleophile, our stupidly strong nucleophile, attacks the least substituted position, and we end up seeing the nucleophile attach that part. Is this a stable final product? No. What can we follow this up with? We can add acid as a step 2, and we would end up with our final product, an alcohol, or RH, with our nucleophile attached. What could be our nucleophile? Carbon could be a good nucleophile. It would be a negative carbon. Okay? Do we know how to make negative carbons? How? Alkynes can act as acids. We can react our alkyne with a stupidly strong base to turn it into a good nucleophile. Okay, would hydroxide work? Okay, our negative oxygen comes off into a solution full of negative oxygens. Is that more or less stable? It's about the same. So not a huge driving force for the attack based on leaving group ability, but what's the other driving force? As a sort of hint with some color, there's no more cyclopropyl ring. We reduced the ring strain by having the nucleophile attack. So I can have a bad leaving group because I'm relieving ring strain by having the nucleophile attack. So negative oxygens work fairly well for this under basic conditions. Okay? Halogens don't work very well. Yeah. What happens under acidic conditions? Sorry. It's advanced. Whoop. Too advanced. What happens under acidic conditions? Okay. The most reactive thing is our acid. We need to neutralize the acid first by having our epoxide give up electrons. What's now special about our epoxide ring? It is charged. Why would it break the other way?
There's a large amount of oxidants to the lower left.
It is a better leaving group. Think back to our bromonium reagent. When we had a really good leaving group, what happened? The nucleophile attacked the more substituted position. Okay? Because that leaving group is already itching to leave. It's already started to pull the electrons away. It's going to pull electrons away in such a fashion that we form the more stable carbocation. Do we actually form the carbocation? No. Okay? But we do start to form some partial positive characteristics. The result is that we get the nucleophile attacking the most substituted position, and we end up with our final product, the inverse of our base reaction. We still get two products out of this. We get, never mind. Why do we not see two products here? Actually coming from that. The reason we got two products before was because we reacted in alkene, okay, which then gets us two products. Our epoxide could form above or below. Where does our attack come in? It comes in below. Nowhere else. It can only come in from below. When would we expect two products out of this whole process? Sorry, I know we're done. Need a quick example here. That's a capital C. Now we expect two products. Why two products now? mCPBA generates two products with our alkene. Those two products then react with our acid and H2O. We didn't see two products on the previous slide because we started with the epoxide. We'd actually already started with it chirally pure or optically pure. Okay? We'll pick up there. Actually, I hate to do this. I'm going to... let me stop the video.